All right. How's that looking?
Looks good. You're good to go.
Okay. All right. Welcome, everybody. My name's Ashley Lubick, and I'll just give you a quick introduction to who I am. I'm a full-time professor at Okanagan College in the Sustainable Construction Management Technology program, and I'll talk about that in a second, a little bit more. I'm also a certified Passive House consultant, and I am the co-director of the Green Construction Research and Training Center, which is a collaboration between UBCO and Okanagan College focused on low carbon solutions for our built environment. Ryan was actually one of my students, so he's a graduate of the SCMT program. And prior to joining the college 3 years ago, I was the community energy specialist with the city of Kelowna, and it was my task to implement the energy step code into our building bylaws. So I've been working at this for some time. So I thought I'd just use this opportunity to give a really quick overview of the program that I teach in. I'm not sure how many of you are familiar with this program, but SCMT, we've been around for about 6 years. We've just undergone a name change and a bit of a curriculum update. We're now known as Sustainable Building Technology, but a lot of our website and that sort of thing has not yet been updated. But it's a program that's taught in the Center of Excellence at the Okanagan campus in Penticton. This is a beautiful building. If you've never been in it, it's worth a visit. It's worth a tour. It's a LEED Platinum building. It went for Living Building Challenge certification, fell short in a couple pedal categories, but a really spectacular building. It's won a lot of design awards. And our program is really, a practical problem-based learning approach, focused on theory, academic rigor, but also a lot of, like I said, applied work as well. And it's taught as a 2-year program. There's sort of 5 main core competency areas: sustainability studies, where we talk about things like building science, energy management, renewable energy, regenerative design, green materials. We have our core studies, that's the civil engineering type stuff, business admin, environmental sociology courses. We have building studies, so we go through things like construction methods and management courses. Commercial studies focused on procurement, quantity surveying, estimating courses. And then our final year, our students undergo a capstone project. So this is really exciting. This is where our students get to work with industry on an industry connected project. We've had students work with City of Kelowna, Fortis BC, High Street Ventures, the Cool Group, Nido Design, working on all sorts of things from embodied energy analysis to doing sort of case studies around energy step code. We've had a group of students do a well building assessment, which is really the complement to LEED, but really focused on how buildings work for the building occupants. So if you want to learn more about this, about the program, you can visit the website, you can contact me. I'm happy to talk about it. And if you are in the industry and there might be an opportunity where you'd like to engage our students through a capstone project, feel free to reach out to me. We're always looking for new opportunities for our students. Okay, so move that here. So when Ryan reached out to me, he had a pretty big ask. He said, can you speak to the importance of RSI values, air and vapor barriers, placement in building assemblies, as well as taking an envelope first approach? And so, as I said, this is a big ask. I have about an hour. I'm hoping to keep it to about 50 minutes so we have a bit of time for questions, but I will do my best. So what I will do is I will give an overview of the envelope first approach, what we mean by that, why it's important. I will really focus on air barriers today because it's important, but I will try to make the connections between vapor retarders or commonly known vapor barriers, the air barrier system, as well as insulation placement and those relationships and the interactions happening between them. And then we'll really take a deep dive into air barrier systems. We'll talk about requirements, materials, strategies, resources, and this will all be reinforced by Alex and his team out at BCIT in their high performance building lab, because they'll be doing some sort of hands-on demos. So I guess their hands, your eyes. And if you have any questions throughout, or you need any clarification, I'll try to keep my eye on the chat. I'll try to do that now. Yes. So yeah, if you have any questions, I'll try to keep an eye on the chat. Okay. First, I just want to give a couple acknowledgements. A lot of what I'm going to be presenting here today is the hard work of the folks at the province, BC Housing, as well as the Energy Step Code Council. So I'll be referencing a number of guides: the BC Energy Step Code Builder Guide, the Illustrated Guide to Achieving Airtight Buildings, as well as this beautiful graphic that's been put together by the Step Code Council that Ryan has already showed you about the 6 proven strategies for high performance buildings. So by now, I think most of you understand what the Step Code is, but really quickly, this is a transition policy that is really trying to create this incremental and consistent approach to achieving better performing buildings. It's really taking us from a set of prescriptions to a performance-based paradigm. So looking at envelope performance, looking at equipment and systems, looking at our airtightness. And there are metrics that are associated with each of those. But as you can see, envelope airtightness is really taking that envelope first approach. And of course, as Ryan said, with the IDP, this has a big impact on the sizing of our mechanical systems, for instance. So it all works hand in hand. I thought I would just connect what the metrics are within the Step Code to these 6 proven strategies. So at the top here, we have boosting insulation, banning bridges. So we're really talking about the amount of insulation, we're talking about the placement of that insulation, and then some of those details to reduce the thermal bridging. And what this has an impact on is our thermal energy demand intensity. So, how much heat we're losing through our assemblies. And then the next piece to the right is really around airtightness, the seal it up, thinking about doors and windows. So we're thinking about, okay, once we've placed insulation, what are all of the other pieces that really control, especially airflow, and doors and windows, not just from the selection of those doors and windows from sort of double or triple pane or the thermally broken spacers, things like that, but also how those doors and windows are installed and how they're detailed, and even the characteristics of those. But we'll come back to that a little bit later on. And then the last piece, and this thermal envelope as well as the airtightness also has a big impact on our mechanical systems, right? And so this is our mechanical energy use intensity. So how much energy is being used by those systems to keep us warm, keep us cool, and to ventilate our space so that we get fresh air. So that's really the connection. And so today, what I'll be focusing on, and can you see my cursor? I don't use Zoom so much, but when I move my cursor through the slide, do you see it?
Yeah, we can see it, Ashley.
Okay, great, thank you. So today we'll really be focusing on airtightness, but we can't look at these things in isolation, right? Everything is connected to everything else, but you'll see why airtightness is of such importance. So what does it mean to take an envelope first approach? First thing we need to do is define what we mean by the building envelope, or what's sometimes known as the building enclosure. So really, this is any part of the building that physically separates the indoors from the outdoors, right? And so, you know, when we look at this, we're really talking about the thermal envelope, our Teddy measurement, as well as our air tightness. I will note that not everything within the enclosure or the building envelope is conditioned. You know, we could have an unvented attic, which would be unconditioned, but it's still important that we understand how heat, how moisture, how air, vapor, whatever is moving through these assemblies so that we can design for them and detail them properly. So that's what we mean by the building envelope. So it's really focusing on those things that affect the envelope as well as air tightness. So we expect our building envelopes to do a whole lot of things, right? They don't just manage heat, air, and vapor. They also, you know, are dealing with radiation, noise, fire separation, durability, aesthetics, you know, all of the design components. They have to be economical. They have to be constructible. They have to be maintainable. There's new emerging things, thinking about embodied carbon, things like that. So our building envelope has to do a lot. But, you know, if I can break it down for the purpose of this discussion today, really 4 things jump out. A well-designed enclosure does 4 things well. It keeps the water out. It controls airflow in and out of the building, keeps heat in or out as desired, right? As well as it controls and allows vapor migration. And we'll get into those things shortly. So, you know, this is what's important to me. You know, if you're a designer, of course, these things need to be important, but you may have more of a focus on, let's say, the aesthetics, for instance, or if you're a builder, you want to do this economically. You know, Joe Seesbrook, I've heard him say that, you know, architects are constantly trying to bring the outdoors in, and building scientists are constantly trying to keep the outdoors out. So we're trying to play this fine balance, you know, between these different needs and desires. So this is a great quote, and it really stresses the importance of getting this right, about sequencing, about integrated design, about good communication, because it's seldom possible to deal with radiation, heat, air, water vapor individually. We have to deal with this as a system in an integrated manner. And, you know, this is from Hutchinson and Hangord, 1983. You know, they headed up the National Research Council of Canada Building Research Center. And in fact, this book that they wrote in '83 called Building Science for Cold Climates, when I went to grad school in Toronto in 2016 to study building science, this textbook, which had been written 33 years earlier, was our textbook. And you know, that kind of makes sense. Everything that we know about building science, we've actually known for a really long time because it's all based on physics. And our understanding of physics has not really changed much in the last 500 years. So, you know, this is important, that we can't really deal with these things in isolation. So we need to deal with them together. All right. So when we're putting these things together to serve those 4 functions, keeping the water out, dealing with moisture, dealing with air, you know, we have all of these different assemblies that are coming together, these different types of barriers, if you will. And so, you know, we have our weather-resistant membrane, our, you know, WRB, we have our water shedding surface, so our cladding, we have air barrier, we have thermal insulation, we have vapor retarder. So we're trying to work with all of these different things, right? So they're coming together. And what's really important is that sometimes one material or a layer will do more than one job. And so it doesn't really matter that that's happening. We just need to make sure that we understand how those materials are working in concert. And we also need to make sure that each job is being done. And so, you know, that'll become a little bit more clear as I start talking through this a bit. But, you know, suffice it to say, we really need to balance all of these different demands with the materials that we're choosing to control them. So why are we so focused on air barriers today? So this image really captures it nicely. It's taken out of the Illustrated Guide for Achieving Airtight Buildings from BC Housing. And so what you can see here is that we have all of these different critical barriers, which we just talked about. We have all of these control functions. So we're dealing with liquid water, we're dealing with air, we're dealing with heat, we're dealing with vapor, water vapor, sound, fire. The air barrier system, as you can see, interacts with virtually every single one of these control functions, from fire through to water, and especially has a primary relationship with vapor, water vapor. So think vapor barrier, heat, our insulation, air, our air barrier, or our air barrier system. So that is really why this is important. The other thing is the air barrier. A lot of it has to do with sequencing, good detail, attention to detail, communication. Really, it's one of those things that we don't have to spend a whole lot of money to do a lot better job with. It doesn't require that we add additional insulation. It doesn't require fancy systems. It really asks us to think about how air moves through the assembly and to detail it appropriately. This is a great little succinct quote: "The air barrier is the envelope." Okay, just keeping an eye on the on the chat. So that's why we're focused here on airtightness, because it is really, that air barrier system is really critical in addressing all of these things. So again, why is this important? Air moves so many things. It moves heat, moisture, pollutants. So when we're talking about heat, that unintentional airflow through the building enclosure can account for as much as 50% of space heat loss. For any of you that have worked with your energy advisor, that have run the calculations, turn the dials on the air tightness of your building, you see what an impact it has on your mechanical energy use intensity, for instance. It can also lead to discomfort. Moisture. So when we're talking about air, and I'm going to get to this in a minute, moisture, there's the liquid water, there's the capillary stuff, it's all of this sort of detail. But when we're talking about moisture, we're often talking about water vapor, which is being controlled by the vapor retarder or the vapor barrier. And then we're talking about convection. So all of that warm, moist air in our northern climates in the winter that's being forced out through holes in our building enclosure. Well, that air carries, as much as 100 times more moisture than is transmitted through diffusion. And so that uncontrolled air, it can get deposited within the assemblies, causing condensation. And so if you've ever opened up a wall, you often see the air leakage pass where moisture has gotten in and created all sorts of problems. And so we want to control for this. The other thing that's, I think, becoming increasingly important is that air carries pollutants. It also carries noise, but pollutants, so things like smoke, forest fire season, any of that air that can penetrate the building envelope comes in, carries in, and creates problems and health problems for us as well. So, air tightness is really important, that heat, moisture, as well as pollutants. The other thing that I really want to emphasize, and this is really critical, and this is where things get a little bit complicated, because you'll often see images like this, and they are really helpful, calling out the air barrier. But the thing that we need to understand is that air is controlled through an entire system. So that's why I like to refer to it as the air barrier system. Okay, so the air barrier material, it only makes up one part of the wall assembly, and it really needs to be designed in conjunction with all of those other control layers. So insulation, the vapor retarding layers, cladding, structural systems, And also understanding that we are going to have items that penetrate that airtightness layer, and we need to detail for them appropriately. The other thing that I will say is that there is no one air barrier material. It can take many forms. And while every air barrier material has to be air impermeable, so it can't allow air to go through it, otherwise it doesn't work, it can have a bunch of other functions. So it could be vapor permeable, like a house wrap. It could be non-vapor permeable, like sealed poly. It could be insulation. So it could be, a couple inches of XPS or extruded polystyrene. Well, that's an air barrier, but it's also insulation. And, like I said, it could also be a water resistive barrier, which happens to be vapor permeable. So, we have to be really careful about what our air barrier material is. And when we're specifying it, we need to make sure that we understand what it's doing with regard to vapor. So let's go through a really quick little lesson. What is the difference between air and vapor barriers? This is the #1 building science question, and it's one of the areas that gets the most confusion around. So I've tried to make this really succinct. I created this little table to really try to capture this, and I hope you'll come back to this presentation, take a look, sit with this. But first of all, we need to understand that air is driven through air pressure. So we have wind forces, we have stack effect, we have HVAC that causes air to move through our assembly. That air barrier, that air is moving heat, it's moving moisture via convection, and it's moving air that's carrying other things like noise, like pollutants, for instance. The other thing we need to understand is with an air barrier, it has to have that continuity. It has to cover every little bit of building envelope to work effectively, every square inch. And where we put it is actually quite flexible, and we'll get to that when we start talking about air barrier systems. So we see all sorts of different materials being used for the air barrier material. We have sealed poly, taped weather-resistant membrane, taped sheathing. And so that just kind of gives you a little bit of a summary of what we're dealing with air. It's being moved by air pressure. On the other hand, we have vapor, which is really, it's water vapor that is being forced through vapor pressure through porous building materials. So it's that moisture laden, or it's that moisture that's in the air that's moving in vapor form through the building material very slowly. And if it's not being slow or retarded, it will simply move from the inside to the outside, depending on what our vapor pressures are. And so that's diffusion. It's vapor. It's not water in air. It's water in a vapor form. The interesting thing about a vapor retarding layer, the vapor barrier, it doesn't even have to be continuous. So a 95% coverage with a vapor retarder layer is 95% effective. This is not the case with the air barrier. The other thing is we generally put this on the warm side of the insulation. So in our cold climate, this flips when we're dealing with hot, humid climates that are cooling dominated. But for all intents and purposes for here, we generally put that on the inside of our buildings on that warm side. So we can use poly, 6mm poly, latex, certain latex paints, aluminum or craft face insulation products, polyiso, things like that. And the reason this is important is because if we don't understand how we're controlling this, if this is too vapor permeable, those porous building materials will allow vapor to travel through our building. It will hit a cold surface, it will condense, and it will create moisture problems within our assemblies. We can get mold, we can get rot, we get all sorts of durability issues. So we need to be thinking about both air and vapor together when we are choosing our materials. So a little bit more on that, just to give you a sense of the importance of this particular topic. And so this is a study that was done in a cold climate. So we're looking at an average outdoor temperature of 18 degrees Celsius with measurements over an entire month. So we have an interior condition that's room temperature, 21 Celsius, 35% relative humidity. Outside, I said, minus 18 average temperature across that 1 month period, 80% relative humidity. We have 3 walls set up. We have vapor diffusion control. We have a class 2 vapor retarder, and I'll talk about what that means in a bit. And what you can see is by vapor only about 3 tablespoons of moisture have moved through that class 2 vapor control layer over that month, okay? If we look at wall 2, where we use a more vapor permeable layer, so we're allowing more moisture to travel through over that same time period, 2.4 cups of moisture have gone through because it's not retarding as much moisture as with wall 1. That's quite disastrous. If we look at wall 3, now we're only looking at air leakage. We're not talking about vapor diffusion. We have a class 1 vapor retarder. So we have poly, it's blocking everything. But we have a 1-inch hole in this assembly. Well, what happens is that air pressure differential is driving moisture through this air permeable insulation, travels out, hits that cold sheathing, and we have accumulated 98 cups of moisture in that assembly, which is disastrous. So this really speaks to the importance of our air barrier system, and choosing the right type of vapor control for the situation. So I'm going to try to, get this to sink in. This was something one of my professors at Ryerson taught me that I never forgot, that vapor is like zombies and air is like a rabbit. So, or like bunnies. And so this is a much simpler mechanism. We're basically we have a pressure differential inside and one outside. And generally that vapor pressure is moving that vapor from higher pressure to lower pressure, from inside to outside, from warm to cold. And, it's just moving in a single direction. On the other hand, we have air, and it is sneaky. It will find the hole. It will travel in one hole, and it will just distribute it throughout an assembly, trying to find a path out. And what it generally does is it hits that cold vapor or that cold sheathing and deposits and creates moisture problems. So remember, we're talking about cups of water or tablespoons of water over a month versus many liters through a tiny hole. So air's like bunnies, vapor like zombies, okay? 10 Pascal is relatively low. That's a pretty standard operating condition, Jerry. Okay, just a few more things about vapor retarders, because this is really a lesson about air barriers. I really just want to emphasize that we need to be thinking about these two things in concert. So what one needs to understand that everything retards vapor to some extent, right? And only things that are class 1 vapor retarders should technically be called vapor barriers, because under normal operating conditions, they are blocking almost all moisture that can travel through. So we have class 1 vapor retarders, and we're going to go through some examples of what different materials are and what their different classes are. We have semi-impermeable vapor retarders, and then we have semi-permeable. So class 1, class 2, class 3, or things that are completely permeable. So you can come back to this, but just understand that, we have some different units. We have the metric nanograms per Pascal per second per meter squared versus US perms. the point is we're just jumping orders of magnitude in terms of permeance. And so what are we talking about here? So if we look at, a product like Blue Skin, this is a vapor barrier. If we look at 6 mil poly on our interior, that is a vapor barrier. And remember, we're only talking about vapor right now. We're not talking about air. If we look at fiberglass insulation, it's permeable. If we're looking at 1 to 2 inches of XPS, it's a class 2 vapor retarder. So it will throttle and allow a little bit of moisture to move in and out as the conditions change, versus a vapor barrier. If moisture gets in between 2 vapor barriers, you have what's called a vapor sandwich, and you can get all sorts of issues, because if there's any unintentional wetting, if there's a breach in your air barrier system and moisture gets in, it will get trapped. It has no opportunity to dry out. So we want to be choosing these materials so that moisture, if it gets in, that unintentional wetting, that it can dry in at least one direction. And usually in our climate, that direction is towards the outside. If we look at 8 inches of concrete, we're talking about a class 2 vapor retarder. If we're looking at any of the building wrap, Typar, Tyvek, they're actually permeable. They're higher than even a class 3 vapor retarder. They're fully permeable. And plywood's really interesting in that it is really a smart vapor retarder. Under conditions of about 40% vapor relative humidity, it's moving about, it's acting like a class 2 retarder, so it can move a little bit of moisture. But as it gets wetter and those pore spaces tend to open up, it will become a class 3 vapor retarder, so it will dry out more effectively. And so, the lesson here today is that installing the incorrect vapor control layer in the incorrect location can lead to premature enclosure failure. However, you need to understand that air leakage is usually a far more powerful mechanism of water vapor movement, okay? So if anybody has any questions about that, we can address them at the end. But this is really important that we are, working. We're choosing these materials, understanding that when we're choosing our air barrier, which a lot of us are thinking about these days because we're thinking about air tightness, we don't want to lock up moisture in our assembly, so it has no opportunity to dry out under those events where we have wetting. That could be built-in moisture, it could be a leak, it could be a breach in the air barrier, and nothing's perfect. Some moisture will get in, so we want to permit some drying. Last thing, the tie-in with insulation is that all of these problems with our buildings, the reason building science has become such a discipline is because we started insulating our buildings from the inside. And when we did that, what we ended up doing was creating cold sheathing. And when we have cold sheathing, what happens is vapor in the air, vapor through our materials, that diffusion travels through those permeable assemblies, hits that cold sheathing, and it condenses and it creates problems. It can lead to rot, mold, all sorts of things. Now, this is a problem. Any air that gets in here, this sheathing is effectively the same outside temperature. So if it's -10 outside, that sheathing is probably -10, maybe -9, but it's going to condense. There's going to be a dew point at the back of the sheathing. Now, and we're starting to see this with high performance assemblies, anything that I work on that's passive house, we're starting to see insulation put outboard of our sheathing. What that does is it moves that dew point temperature into the middle of the insulation rather than onto the sheathing. So there's no condensation point for that moisture to accumulate. So this really approximates what is known as the perfect wall, where we have the structure of the inside, we have our control layers and our insulation on the outside. And so you know, if you want to learn more about this, there's some great stuff in this builder's guide on insulation placement assemblies. But just remember that a lot of these problems have been created by putting the insulation on the warm side, the inside of our buildings, on the inside of the sheathing, which creates moisture problems. Okay, so we've talked a little bit about air barriers. We've talked about vapor retarding layers, vapor barriers, different materials, and we've talked a little bit about insulation placement. So I just want to, you know, we have a couple minutes here. I'd like to do just do a little knowledge test, and I don't have a fancy Mentimeter like Ryan. I'm used to a different platform where we can do sort of pop quizzes, but what I want to do is, you know, and feel free to jump in, turn on your mics, use the chat. What are we controlling here? And keep in mind that let's focus on only what we can see. Let's assume that everything that is in the picture continues elsewhere, because, you know, in terms of continuity, that is really important. So what are we trying to control here? Air mostly? A? Okay. A, anybody else?
Anybody feel free to use your mics if you want to.
Okay. Martin said C, air and vapor. Okay. All right, we're going to move through these quickly, just in the interest of time. So, C, why is that? Well, this is an air, OSB's air impermeable. So it's part of the air barrier. It's taped. That's a really good hint. We've taped all the seams, all the intersections, all the joists, probably, hopefully the penetrations. So the other thing is OSB is also a type 2 vapor retarder. So this layer, there's no poly in here. This is throttling, controlling the vapor, as well as detailing and sealing for the air. Okay. Next one. What's being controlled here? So we have Tyvek. Could be Tyvar. What do you think is being controlled? Is it air? Is it vapor? Is it liquid water? Is it air and vapor? Is it air, vapor, and liquid water? Anyone? Is this one stumping you? Okay, air. Keep them coming. Okay, I have one for air. All right, well, if nobody else is going to jump in, liquid water, from what we can see. So, you know, chances are this is probably mounted to some sort of substrate like OSB or plywood, but we can't see it. In that case, you know, it could be taped, that plywood, that sheathing could be taped, and then it would be controlling air. But from what we can see here, because this Tyvek is not taped, it's just lapped, air can get in. It's permeable to vapor, so it's not controlling vapor. It's our water resistant membrane. It's controlling liquid water. So anything that gets in behind our cladding, that deals with it. So just liquid water. Now, if this had been taped and continuously tied in, then we could have said that it was dealing with both air and liquid water. Okay, so we want to be looking for these clues. Okay, we have two more. So I'm not sure how many of you are familiar with the zip sheathing system, but what do you think we're controlling here? Air, vapor, liquid water, air and liquid water, air, vapor, liquid water. Anyone?
Looks like we got some shy people today.
Okay. Air, vapor, and liquid water. Okay. E. Okay. All right. Well, I would say E is mostly true, but I've selected D only to say that, you know, this green coating that is bonded to the OSB is really controlling the liquid water. That it's taped and that this OSB is air impermeable is an indication that it is also the air control layer. The reason that I didn't say that it was the vapor control layer is because if this is being insulated from the inside, I would hope that we have another vapor control layer that's helping to throttle that moisture-laden air that's coming through the diffusion from the inside, because we generally put our stronger vapor retarding layer toward the warm side in cold climates. So that's why I said air and liquid water. I would hope in this assembly that there's something else going on in terms of dealing with vapor from the inside. If this got mounted with exterior-based insulation, you know, let's say 4 inches of Roxol, for instance, then certainly E, that it would be serving all of those functions. Okay. One last one. We're starting to get a little bit more complicated. So this is extruded polystyrene, XPS. Well, you can see it's got some tape on it. So what is it? What is it controlling? G, F. Yeah. This one again, you know, we don't have enough information to really know, but there are a lot of hints. I've chosen G. Part of the reason is because depending on how much, assuming this is only 1 inch, probably the answer is F, or sorry, it's the answer would be a combination of air, liquid water, and heat. When we take a type 2 vapor retarding layer like XPS at 1 or 2 inches, if there's 3 or 4 or 5 inches of that material, we start pushing it closer and closer to a class 1 vapor retarder, which is also a vapor barrier. So if let's say this was 6 inches of XPS insulation outboard, and then we put poly on the inside, well, we could end up with a vapor sandwich that we were talking about. So it's really hard to know. What we can say with absolute certainty is this is controlling air because it's taped. It's controlling liquid water because this is acting as our drainage plane, and it's dealing with heat because it's an insulation product. It could also be, and like all materials, it's also controlling some vapor. Okay, how strong really depends on the depth of that insulation. Okay, moving on. I know I'm throwing a lot at you, but thanks for your participation. So let's get into the details of the air barrier system. All right, so it's really important, again, that we're talking about this as a system. It's not a single layer. It's made up of layers, it's made up of materials, it's made up of components, things like doors and windows, as well as the accessories. So these are things like caulkings, these are tapes, these are self-adhering membranes, these are roll-on membranes, and how these things work together. So how they lap, how they you know, interface, how they, you know, tuck under our assemblies really determines how well our air barrier system is going to work. Okay, so materials, components, as well as accessories. Oh, I think I skipped over. Okay, in order for something to be an air barrier, it has to be continuous. I think I've beat that one over the head enough now. So, you know, it has to span assemblies. It needs to deal with all of those penetrations. It needs to deal with transitions between different assemblies and different materials. It has to be air impermeable. So for a material to work, and this applies, that air impermeability is not just specific to one thing, but the whole system. So it has to be our components. It has to be our accessories. It has to be the materials. Everything has to be impermeable to be part of that air barrier system. It also has to be durable. So there has to be that resistance to moving, fatigue, temperature change, UV, anything that it might be exposed to. That durability needs to extend over the life of the service life of that material in use, and hopefully for the life of that building. That stiffness is also, really important in that, if we get any sort of wind loading, you can imagine that if any wind gets in behind even a taped weather-resistant membrane, and there's a mechanical fastener, if that can pump and rip loose, then then we have a breach in our air barrier, and so that's a problem. So I like to say that the best air barrier materials are those that you need to get a saw out for. So we want things that are stiff. So plywood, OSB, some of our insulation products, they're better than, let's say, poly or even a weather-resistant membrane. Although we can, because a weather-resistant membrane is supported by sheathing generally, that can also be quite stiff if we do it well. It needs to have strength, and so both structural integrity, again, against rips, things that might happen because of different pressures put on it, but it also needs to resist those dimensional changes. So wood is expanding and contracting with different moisture. So when that moves, is that air barrier, are those sealants, those caulkings, those tapes, are they able to resist those dimensional changes? So we want to think about that. So again, this is taken from the guide. And then I also say they need to be compatible. We need to make sure that if we're using a tape, that it's meant to go on whatever substrate that we've identified that it should bond to. Because there's all sorts of tapes on the market, but that might be air impermeable, but if they don't stick to OSB, for instance, they're of little use. So to go back to something I said a bit earlier, air barrier materials can be all sorts of things. The number one thing is they need to be air impermeable. The air can't go through them. But as I said before, some air barrier materials are weather-resistant membranes. Some of them are strong, they're vapor barriers. Some of them are vapor retarders. But we've gotten that out of the way. Now we're really focused on, okay, what constitutes an air barrier material? So there's this nice chart that came out from the CMHC in the early 90s that just really lays out all of these different common building materials and where they land in terms of their air permeability measured in liters per second per meter squared at 75 Pascal. And so for something to be an air barrier material, and this is called out in the building code, it has to be less than 0.02 liters per second per meter squared, okay? At 75 Pascal. So there's ASTM standards that dictate this, but you can see that, all sorts of materials from, insulation boards, foil-backed urethane insulations, XPS, plywood sheathing, gypsum board, they all meet this criteria. Thinner particle boards, for instance, well, it's not even that thin. Hardboard, for instance, 3.2 mil doesn't meet the criteria. Roofing felt doesn't meet the criteria. So just make sure that when you're using air barrier materials, that they meet the criteria. All right. In terms of the air barrier strategy, continuity is key. We need to be, again, thinking about those interfaces, those joints, those intersections, the penetrations, and one should be able to take a red marker, draw it across the entire exterior of our building envelope without ever lifting that pen, showing that continuity. So we want to make sure that our air barrier is continuous across all of those. It should wrap, under our building, below grade walls, above grade walls, across windows and doors, through our roof assemblies. And we'll get into some of these strategies in a second, but just remember, continuity is king. Now, when we're talking about better and smarter envelopes, time and time again, it's been demonstrated that exterior air barrier solutions are easier to execute and they have better performance than interior approaches. Can we get decent air tightness with an interior poly approach? Yes. Is it as effective? Is it as easy to execute? No. We have more surface area. We have more penetrations. We have electrical. We have plumbing. We have all of these. We have walls that are, interior walls that are abutting. We have all sorts of issues from the inside. It just takes more time, and the sequencing is much more difficult than, if we take more of an exterior house wrap. So I'm not talking about house wrap as in Tyvek, although that might be one of the solutions, but using things like, taped plywood, taped OSB, roll-on or self-adhered membrane. Those can be more effective, less surface area, easier to execute. Or on the interior behind a service cavity. So this is an example, OSB that's taped, furred out wall. So all of our services get run, no holes are ever put into this air barrier. And lastly, just with respect to these tie-ins with these 6 metrics for better and smarter buildings, thinking about windows and doors, air tightness is critical. We want fewer sliders, so it's also through the windows. It's the quality of the window and the connection. So you can, those felt gaskets, those sliders. They're leaky. They don't have the same sort of resistance to airflow as, say, a compressed seal that we find in a casement. So trying to move away from sliders to more compressed seal type units. And then that installation detailing is also really important. So, it's not just the quality of the window, but it's how it's installed. Okay. So now I'm just going to quickly go through, and this is where Alex is really going to show some examples of how we do this out in the field. But we're going to talk about some of the strategies, exterior approaches, interior approaches. We'll talk about below grade and slabs, as well as roof assemblies. Again, this is all taken from the Builder's Guide. So we have taped sheathing membranes. So this is a weather-resistant barrier. So where we see the pink and the red, these are indicating our air barrier strategy. So we have well-supported weather-resistant membrane that's taped and continuous through the entire building enclosure. Another way to do this is to simply tape or use, some sort of a paint-on product to deal with our sheathing. So we've taped the seams of our sheathing, and then our weather-resistant membrane, we just lap it normally. No need to tape it because the air barrier has already been dealt with. We've seen this approach in our picture. We can also do sealed exterior insulation. So we're insulating, we're keeping our sheathing warm. We are taping. This is air impermeable. We're taping it, and this is also serving as our weather-resistant membrane. It's that last line of defense, protecting our sheathing from any liquid water that gets through our cladding. And then another approach there's all sorts of new products on the market. These liquid applied air barrier solutions from Prosoco, is it? I believe. This sort of liquid applied approach can be basically painted on over the seams with the sealed exterior sheathing. It can also be put on to cover the entire sheathing and assembly. It's airtight, and it also serves as the weather-resistant membrane. And so, those are 4 common strategies for our air barrier. When we go inside, most commonly we have sealed polyethylene, right? We have the Black Death, the acoustic caulking. We have a number of tapes. Again, we just need to make sure that everything's being lapped, it's being sealed, that no air can, basically sneak in behind it. Detailing around all of these penetrations can be really, really tricky. And this is a much more difficult one to execute. This is not a bad interior approach. Sealed interior sheathing, we just saw an image of that not too long ago with a service cavity. This can make for a really good approach. Interior spray foam, so long as it's closed cell, making sure that it is indeed air impermeable. This requires that we're really thorough, that we have good coverage, good depth. All of those intersections are being sprayed appropriately. And then we also have to remember that, if we look at our top plates, for instance, that air can also bypass, this only deals with this rim joist or this wall cavity. We also have to caulk or seal between these wooden members, no matter how tightly they're fitted. So we need to make sure that, again, this is continuous. So we've sealed the entire exterior wall. And then lastly, and we don't see as much of this in North America, but this is the airtight drywall approach. So we're using a series of gaskets, our mud, that sort of thing, and just making sure that air isn't able to sneak in between or under these sheets at the top of wall, bottom of wall, or at our corners. So airtight drywall approach, a little bit less common. And then this can be painted with a vapor retarding paint to deal with the vapor component. All right, so last two things, roof approaches, and then we'll get into our below grade and our slab. So this is a self-adhered sheathing membrane. So again, this is, because it's self-adhering, we don't need any tape. This is serving as our air barrier layer. Needs to, our primary air barrier layer, we just need to make sure that it's, continuing with the rest of that air barrier strategy. We see sealed polyethylene. Again, this is a trickier one to execute because in this example, we have a pot light. We have to penetrate the air barrier layer. So we have to detail, we have to tape it. We have to make sure that that's well supported. It makes our lives a little bit more difficult, but as it's one of those approaches that are more common. A better approach, and what I see more in the passive house world, is a service cavity. So we're using something like plywood or OSB as our primary air barrier material. It's taped, and then our service cavity allows us to mount, any of those surfaces that we need without penetrating that really important layer. Okay. With our below grade approaches, keep in mind our concrete is air impermeable. However, over time it can develop cracks. So if we get a crack in that layer, then our air barrier layer is compromised. So using concrete with an air barrier membrane is a good idea. Caulking around any penetrations, insulating from the exterior makes a whole lot of sense. Sometimes we have sealed membranes. So for example, 15 mil poly, again, any cracks that develop, this is being dealt with by this poly. This is basically something that we see with radon systems anyway. So, and this next picture over also taken is really just showing that between the concrete as well as the, let's say 6 mil poly or what have you, those two things are working together as our air control layer. Lastly, if we're using something like XPS that's air impermeable, we can simply tape it. We connect it to the perimeter for that continuity, and that becomes our primary air barrier strategy. And again, we can also rely on the slab for a bit of redundancy. Okay, I've already talked a bit about this, and Ryan has really beat this one on the head in terms of the integrated design approach, but we really want to get that early detailing down to a pat. The overall design process, the sequencing, using 3D drawings, getting our architects to make this really dead simple, because where things lap, where things are coming together around windows, between floors. It's really important that everybody that's trying to execute this strategy knows exactly their role in carrying it out. We've seen some really good stuff. One of the things the guide talks about is appointing an airtightness boss. Somebody that if there is a breach, if somebody makes a mistake, it gets reported, it gets dealt with. I've worked with a company called High Street Ventures, and they've done some really great stuff. They've put together a little airtightness orientation, just like a safety orientation that they do with their crew. And every single person that touches that building envelope has to go through it. They get a little sticker that they put on their construction helmet or on their vest. And it basically goes through, these are the things that we're doing, these are the things to report, and these are the things to avoid. And so, that sequencing and then managing all of our trades and our subs on site is also really, really critical. And little things like this, like an airtightness orientation, can make all of the difference, because you guys are all here at CPD points, but one of the things that's often missing is we don't see our subs in these sessions. And so they're often the ones that are filling holes, cutting poly, stapling where they shouldn't be, cutting where they shouldn't be. So that's really important. I see that there's a question. I'll come back to that in a second. I suspect Alex will talk a little bit about this, but really, again, we're talking about interfaces, penetrations through our assemblies. And so if you look in the guide, these are our common deficiencies, our common air leakage paths. I don't think any of you would be surprised by them. They're rim joists, cantilevered floors, plumbing stacks, pot lights, wall-to-ceiling details. We need to get these right. And these 3D images are really useful. And if you need more of them, we have the Builder's Guide that really shows these beautiful sections for all sorts of different assemblies, from windows to sloped roofs, low sloped roofs, rim joists that supported balconies, which is important because even if we're doing an exterior strategy, there's opportunity for interference with our air barrier layer for anything that cantilevers or is supported, as well as these below grade solutions. So I really encourage you to have a look at the Builder's Guide. It's freely available and just a really great resource. Another great tool comes out of the Illustrated Guide for Achieving Airtight Buildings. Again, this came out in 2017, BC Housing. They have these checklists. They have a design checklist, they have a construction checklist, and then they also have a testing checklist. So you can go through these with your design team, with your construction team, make sure you're identifying who's responsible, who the responsible party is, what the completion date is meant to be. These can be really useful in terms of having good job site management and good sequencing as well. And then BC Housing Province and City of Vancouver have also come up with this really nice one-page wall air barrier reference sheet. So all of the common sort of intersections and interfaces and how to deal with them properly. So you can print this off, circulate it, and here's a link to it as well. So some really good resources. This is what it looks like up close. And I will say that I know BCIT, they also have their key concepts for zero energy buildings, their air barrier installation for zero energy building, and their membrane reference table guides that I'm sure they'll speak to you about. So lots of really great tools out there to assist with you getting this right. So I'm just wrapping up now. Just to recap, we've talked about airtightness, we've talked about Vapour, we've talked a bit about insulation, but that airtightness drives 2 of the 6 high performance building principles and really influences a 3rd. So, we seal it up, we think about those windows and doors, think about the installation, think about that continuity, we can really deliver good buildings and good systems. And, I know Alex would agree with this. I say it influences a 3rd because when we make our buildings airtight, we need to make sure that we're getting fresh air to our occupants for overall overall health and well-being, and also for dealing with things like moisture and recovering energy, so that we're getting the benefits of putting all that effort into our air barrier strategy. So I'll just say good air tightness demands good controlled ventilation, balanced ventilation. So we want to stay away from exhaust only or supply only ventilation systems, and really start thinking about HRVs, ERVs, and bringing in that fresh air for our occupants. So we covered a lot. I hope your head's not spinning. I think a lot of what I've talked about will be reinforced when Alex gives the demos. But just a quick recap. Air leakage is usually a far more powerful mechanism of water vapor movement than diffusion, but you need to understand your overall moisture management system, how the air barrier, how the vapor retarder layers, and your insulation impact the total health and durability of your assembly. Air barrier system needs to be continuous to be effective. Vapor retarder layer, not so much. Air barrier system, an absolute must. Detailing is an integral part of the design process. And like I said, lots of resources out there. Spend time with them, share them with your teams, do some training, get your subs involved. So that's all I have for you. Any questions? I think I saw a chat question. Air barrier question. Are air barriers at risk of reduced performance over time? When TV pictures, shells are mounted, moved, removed, does this change? So you're talking about holes through the poly, for instance, or through any of those. How significant? If it's a finishing nail through the poly, it's not enormous, but it's best if we can leave that air barrier material alone, that we're not putting penetrations through it at all, regardless of their size. And I'll let Alex, speak to this a little bit more, but in terms of significance, I would say no, but the more that we do it over time, the more significant it becomes. Yeah, I would agree with you, Simon. Redundancy in air barriers is welcomed, not a bad approach at all. You generally just want to have one strong vapor resisting layer, and that's generally on the inside of our building. We don't want to sandwich, especially. Yeah. Okay. I think that's my time. I will be here till the end of the session. So if anybody has any other questions, we can address them at the end. I'll hand the floor over to Alex and his team. Thank you.
I'd just like to say thanks, Ashley. Once again, you're always a wealth of information, and I encourage anyone that has future questions or wants to learn a little bit more to maybe reach out to the Okanagan College and Ashley and the other professors there with the SCMT program. They have a lot of good information on hand. So that being said, Alex, how are you doing there?
Can you hear me, Ryan?
I can. So.
Okay, awesome. Ryan, we're ready to go. I made a note yesterday when we did our dry run, we would take a 5-minute break. I'm fine with a break or no break version. It's as you prefer.
Yeah. Well, why don't we just take 2 minutes if anyone has to run and use the bathroom real quick, and then we'll get rolling right away here.
Okay.
So.
Okay, perfect.
Yeah.
Okay.
All right, Alex, anytime you want to go, you might as well. Perfect.
Okay, so I just unmuted myself, Ryan, so I'll just double check that you can hear me.
Yep, we can hear you. I can see your full screen. I think everyone can see a full screen, so I think you're good to go.
Perfect. We're good to go. Okay, thank you. And I guess that's the first thing. Thank you, Ryan, for inviting us to be here today. Thanks, Ashley, as well, for doing kind of the legwork for us to get everybody on the same page on the science of, I guess, the science of buildings in general, but the science of air barrier and the relationship with moisture and other components. So my name is Alex. I work at BCIT. I'm part of a fairly small team called the Zero Energy Buildings Learning Center. I'm in our classroom. It's not a classroom anymore. It's a broadcasting studio because with COVID, we've been asked, to keep students at home as much as possible. So we're usually here, 3 or 4 of us with cameras, and we teach from here, but the students are at home. So maybe Mary can kind of quickly give you a bit of an overview, but it's an old, it used to be an aircraft maintenance. It used to be a workshop used for aircraft maintenance, and it got turned into a building science classroom a few years ago. And what you find in the room is a bunch of wall mock-ups. There's a 2-story house in the middle. We have, Ashley was reminding us how important ventilation is if you're going to build airtight. We have a few heat recovery ventilation systems that are operational that we use for teaching how to commission system, how to system balancing, and so on. And really what's happening these days with COVID is that we're trying to keep our courses as hands-on as possible, except that the hands that are getting dirty are not the hands of the students, they're the hands of the instructors. So the students are at home, they get a good seat because they get a first row kind of seat. And our instructors are building things in front of the camera or disassembling things in front of the camera, and students get to see the sequencing, get to see details that are sometimes hidden, and our students get to ask questions. So I was thinking, Ryan, before we get going, we have a 1.5 minute video that talks about what we do. I'm in the lab, by the way, with Vanessa and Mary behind the scene, and then Cody that you saw briefly. Cody will introduce himself in a minute. And I'll go behind the camera for most of the presentation as well. Okay, are we ready for the video? Okay.
The BCIT courses provides a solid understanding of the principles of high-performance building.
We go through the step-by-step. You have a vented deck assembly up top. How do you transfer the air barrier not only through here, you come up the wall, how do I get it back over the deck area to the wall in behind in a continuous manner? There's not this fear or uncertainty attached with, the PowerPoints, and it's a very practical approach to show exactly how that gets done.
As an online participant to this specific program, I did feel like I was in the front row all the time in every session.
Just to learn the tips and trades and not just be driven by theory and PowerPoints.
You have to get down and talk about the details, show people how these things work together.
I'm James Bourget, part-time instructor at High Performance Lab at BCIT.
Part-time lecturer here at BCIT.
A proud partner and sponsor of the BCIT High Performance Lab.
I'm an architect in Vancouver and also a BCIT student.
Red Steel Carpenter, high performance tradesperson and student at BCIT.
Cut.
It's funny, the video shows Cody as a student, I guess. He was such a good student, we heard him. So we'll have to redo the video where it says instructor. So yeah, it gives you a bit of a feel for what we do. So what makes me very proud about the courses here is that we have multiple instructors teaching the courses. We have instructors that come from different backgrounds. Vanessa, Mary, and I are kind of behind the scene, and the stars of the show are the architects and the carpenters that have agreed to teach for us a few hours a month. So you get exposed to different folks with different expertise and different teaching styles, and usually everybody finds something that is good for them in the courses. Before I give you the outline for today, the other piece I should say, I'm a mechanical engineer by training. I've been managing energy in buildings for quite a while now, trying to get buildings to be more energy efficient. And for most of my career, I wasn't sure I actually understood what I was doing, and I would try to be quiet sometimes at meetings because the complexity of the discussions were beyond what my little brain was capable of dealing with. And suddenly I heard of this envelope first approach to energy management, got interested into it, and finally got to a point in my life where I truly understand what I do, and it's a pretty good feeling. And so when it comes to adding insulation to wall assemblies and making assemblies more airtight, it's definitely not rocket science. And what you need to do is get a good course, and you're probably good to go. So if you're interested in those courses, just go to our website. It's a pretty easy URL. It's bcit.ca/zero-energy-buildings. If you're not into typing URLs and you like Google, just type BCIT space ZEB. So ZEB in this case would stand for Zero Energy Building. So if you type BCIT and ZEB, Google will give our site as your first option. And the courses are listed on the main page. And then maybe that's my final note. We have courses starting in April. The next courses start, I think, April 20th or something. And our courses are fairly short. So the longest course would end in June. So if you start in April, you'll be done by June. You'll spend time with us roughly once a week, and you'll be good to go for the busy construction season. Okay, so that's kind of it for the intro about us and what we do. Let's talk about what today will look like. It's 9:45. We are keeping 15 minutes at the end for questions and for Ryan to wrap things up. So we have roughly 45 minutes. We are going to divide things into two things. You can see behind me here, we have 5 wall assemblies. So we're going to walk you through these assemblies, thinking of air barrier as the main topic. So the assemblies obviously are showing pretty much everything that Ashley mentioned to you. They all have 5 critical layers. All the layers have been installed correctly. What the walls have in common behind me is they are all thicker than the average code minimum wall. So we increase the thickness of the wall. And of course, with a thick wall comes the possibility to add insulation. So those walls have more insulation than a typical wall. And then the other thing they all have in common, although they look different, is they all have a continuous air barrier system. Again, as Ashley mentioned to you in his presentation. So what Cody and I agreed to do in preparation for this is stick to the air barrier portion. Cody will most certainly make comments about moisture and moisture management, because as Ashley was saying, it's all interrelated. But to be as brief as we can and fit within our timeline, we'll mostly focus on air barrier. What I want you to know before Cody gets going with the presentation, these walls were is a project that actually was led by Natural Resources Canada, so it's an NRCan project, and they hired RDH Building Science to work with them through a lot of industry consultation to come up with wall assemblies that would allow builders to get to a net zero energy ready level without making too many changes to how they build. So all the walls behind us have that possibility of getting you to that step 5 of the energy step code, and they have all been vetted by industry, and they have all been designed by building scientists. So it's a pretty good, it's a pretty credible and solid sources for the walls. And then RDH came to us and said, well, we actually need someone to build those assemblies. We can look at constructability for Ching. And very soon, and we don't know exactly when that is, but very soon NRCan will have published guides that would allow you to kind of look at these walls at home and get the entire information. So we'll keep Ryan posted on when those guides are published, and Ryan will be able to tell you more about it. So that's kind of part one, where we're going to walk you through those walls, looking at the air barrier. And then if we can come to this side here, we're going to then take these, I call them tabletop assemblies. You know, I'm not sure, we should probably come up with a better name, but they're very simple building assemblies that, you know, start with the below grade systems, go up with the walls and go all the way to the roof system. And what Cody will do is he's going to walk us through, in this case, two different strategies of getting your air barrier installed and get your air barrier continuous. So two things, the wall mock-ups and the tabletop assemblies. I think that will bring us to the end of our time. Hopefully, if you have questions, you'll ask them as we go. Between Vanessa, Mary, and I will be able to keep an eye on those questions and relay them to Cody. So maybe I'll stop there. And Cody, before you do a deep dive in the wall, maybe do a full introduction of yourself so people know who you are. And yeah, we'll go from there. Thank you.
Hi, my name is Cody Brenson. As Alex mentioned, I'm a past student here at BCIT. I'm also a part-time instructor, but I also work in the field, run a company called Envelope First to do contracting air barrier strategies. I've had the opportunity in my career to work on many high performance step code compliant builds, as well as past projects, including the daycare in your beautiful city, which is a really fun project. I'm going to spend a little bit of time talking about the 5 critical barriers in these wall assemblies, what their roles are, where they're located, what products we used, but with an emphasis on the air barrier being the primary barrier that we're going to talk about today. As Ashley mentioned, all the factors of vapor migration are fairly important, and we have all these different assemblies that show the different products you can use when you're moving towards a non-prescriptive manner in the code. What's important to note is your interior versus exterior climate is going to drive your decision makings on these barriers and where they belong. So I'm going to take you over to this first leap wall. It's very similar to the Penticton daycare, which is a double stud wall with a cellulose cavity. It's still a cold sheeting approach, and you want to be careful of vapor migration through the wall in the course of construction. This is still your condensating plane, but it actually has an opportunity to dry very quickly to the outside. So when we're talking about our subwall connections, we have our 5 critical barriers. So we're starting with at our concrete, you've got your water resistive barrier that is also an air barrier completely through the whole assembly. So it comes up to a receiver that goes to your Tyvek, comes up when you have a window penetration. It's a very well thought out window penetration with a back angle, a high performance window, and you can see all the layers inside. All the windows have the same thermally broken frames. And we work our way up the wall, thoroughly detailed, and we come to a receiver on the top plate. So we've thought out the air barrier continuation from the foundation all the way to the top plate of the wall. So you have a receiver plate here that goes to the plywood that makes your top plate for the entire wall and then carries through to a poly ceiling. So one thing all these walls have in common is they are all an unconditioned attic. So we're primarily dealing with the transfer at the top plate into the underside of the ceiling for your air barrier for a continued plane of airtightness. As we move into our next wall, our critical barriers, we talked a little bit about what they are, and I'll just kind of explain it on some of these, where your primary source of defense is your watershed surface, which is your cladding. Its primary function is to deflect any water or environmental weather. You move behind, you're going to find that this has insulation on the outside of your weather resistant barrier, which in this case is also an air barrier. So what we've done with the EPS foam is we've actually provided a break between your unconditioned attic space, where your weather resistant barrier above the top plate is strictly just a weather resistant barrier. And we have the same top plate receiver detail to continue the air barrier onto the inside, the underside of the ceiling. Because this is a vapor closed product, there's a little bit of moisture mitigation that through the course of construction, If something was to get behind here in the course of construction or want to dry out as a vapor, we've added a capillary brake to deflect that water back to the outside and evaporate. Same techniques have been taken at the base of the wall with the capillary brakes when you're dealing with an insulated concrete foundation. Everything has been layered from the outside in a continuous manner, so you have a monolithic air barrier all the way up through your window assemblies like in the other walls. Moving on to the next wall here, which has a couple unique characteristics to it. We've used an XPS exterior insulation with staggered joints. So you're actually helping minimize the ability for air movement by staggering your joints in a properly planned manner. But what you'll notice is bare plywood behind here. So this insulation in your 5 critical barriers is actually adding a protective layer of your thermal barrier, your water shedding surface, your weather resistant barrier, and your air barrier. Sounds like a great idea, but you've got to be careful of your climates and what your vapor drive forces are. So if you have anything in the course of construction that needs to dry outward, you've got a couple risks that you might need to manage in your install. It is very good in dry, cold climates, maybe not the best for a wet West Coast region. Again, same principles starting at the bottom of the wall. We've got a insulated concrete form, could represent an ICF foundation or a high density EPS. You've got a subterranean environmental separator that you want to make sure that you have a certain amount of care and you don't put your dimple board on too quickly, because you need to have a receiver transition between here and your wall. So this is actually all part of your air barrier coming up through the window, again, top of wall, transferring through where your air barrier can hit the top plate. Your wood in your construction in your typical 2x6 wall now becomes part of your air barrier system. So like Ashley mentioned, your air barrier isn't something that you're just going to buy off the shelf, put on and call it a day. You can actually integrate many different pieces of material into sequencing a complete monolithic air barrier. It's important to notice on the back side of this one, because our vapor control layer is on the outside of our sheathing, we have no need for a vapor control barrier on the back side of the wall. Now we're going to move into something that people are probably a little bit more familiar with, is an exterior rock wool insulation. The difference between this product and the 2 foams that you see is that it's highly vapor open and vapor permissible. It allows drying forces to the outside of the building. It has many other benefits like being non-combustible. It's fairly easy to work with, but you also want to notice that it's not as dense or rigid as the XPS or the EPS foam. So you want to make sure that when you're tightening in your rain screen straps, that you have a nice flat facade, because aesthetics are still important in what we do. Same principles starting at the bottom of the wall. Exterior insulated concrete. So we have a thermally continuous wall. We started with the same subterranean protection, which is a vapor closed product, coming up to a peel and stick receiver, also vapor closed. There's not a high concentration of wood here, so we're not too worried about vapor diffusion getting stuck behind here, because we've minimized our vapor closed area. We have again gone to a Tyvek, which is your weather resistive barrier and air barrier, which goes up in a monolithic fashion, same as before. Through the window, we've added an extra layer of peel and stick just as a deflective purpose. Even though this rock wool is hydrophobic, you still want to have any moisture that can be caused from intentional window weepage to get to the outside and dry, or dry through your pressure moderated rain screen. We've come up through the wall and the window again in the same fashion as before, thoroughly planning out our install. Might be important to notice on the inside here, part of our air barrier system on all these windows is a rod and caulk connection. Now you want to make sure that you have minimum depths and very continuous seals there, because that is an important part of your air barrier. If you're pre-striping your windows with Tyvek for a sheeting inspection, make sure all connections and overlaps in your Tyvek have been taped properly, because once your window is installed, you can't get back and tape at that, and you can have some air loss. And like Ashley mentioned, air movement is the vehicle for vapor in larger magnitudes than just the diffusion aspect through the vapor drives. So if you have air movement, you can have a lot more water in the wall. So make sure that every lap that you do when you're pre-striping a wall has been thought out, planned, taped, and sequenced. Again, moving up to the top of the wall, you can see we've put some internal cribbing inside for finish backing, which is also thermally broken by the exterior Rockwell insulation. This is all still part of our air barrier membrane. We come up to a receiver. Actually, this one, sorry, has been backlapped with a urethane, which is still a suitable product. You want to make sure that it's not surfactant to the Tyvek so that it doesn't ruin its waterproofing capabilities. So just always keep in mind that your products are compatible with what you're planning to use. Again, it transfers through the top plate and then to acoustical seal to the underside of your ceiling. This also has a standard vapor retarder on the inside that if you're putting a lot of detail into your air barrier, you don't need to continuously seal your vapor barrier. Again, you want to be very careful that you've mitigated all your air losses, that you've got complete air tightness throughout your whole build. You can go a lot lighter on your detailing on your interior vapor barrier where you have dozens of penetrations as opposed to the outside. Alex has a comment to make.
Cody, there was a really good image. If Mary can come back to this image here. You know, I look at this, your Tyvek is taped everywhere. I mean, it's maybe hard to see, but there's a bit of red tape here. And suddenly it's not taped anymore. Can you tell me, you know, what does that tells you?
Yeah, so when you have a break in there at the top of the wall, we have a vented unclimatized attic. So this section of your build, if you understand the red pencil drawing that Ashley mentioned, your air barrier, where that red pencil goes on your build, transfers through your top plate. So you don't need to seal up an area that's uncontrolled or unclimatized, so you can allow ventilation through the attic as we traditionally have done.
So the upper part, the Tyvek below that line is a water resistive barrier and an air barrier.
Yes.
Past that line, at the upper levels, it's only a water resistive barrier. Is that correct?
Exactly, yeah. So the control function of everything below the top plate is a weather resistive barrier as well as an air barrier. But at this transition, this becomes a single function of weather resistive barrier.
And Cody, I'll let you go to the other wall, but if you can stay on that image, Mary, for a second, just keep this image in mind. Ashley said, hey, and Cody repeated it, an air barrier is not something you buy at the store. It's a system. It's a combination of different materials. As long as it's continuous, you know, you're mostly good to go. The connection between the Tyvek, which is the air barrier, and the plywood, and then the top plate is done with acoustic sealant here. You know, that works. And keep this image in mind because on the next mock-up and the previous ones, I don't know if you got that, but you'll see tape was used to do the transfer. You know, they're both okay. They both have pros and cons. But the idea is that if I want to attach one material that is air impermeable to another material that is also air impermeable, I need to use some kind of adhesive or, you know, a connection that is also air impermeable, and it's going to be sticky enough to keep things together. So just keep that image in mind because Cody's going to show you the last wall. And on the last wall, we're not using acoustic sealant for that transfer. We're using tape.
Yeah, that's a great point. You know, just to emphasize that your air barrier is a thoughtful process of multiple products that you've decided to use based on your climate control. So when we move into the last mock-up here, which is my favorite, we can't truly talk about net zero ready without embodied carbon being part of the conversation. So this is a wall that we've created with Chris Magwood from the Endeavour Center that's using primarily biogenetic materials to sequester carbon during the process of its growth to lower your carbon footprint in your build. Couple key differences that we've made in this one is still starting at the bottom of the wall with an exterior insulated concrete foundation. Still have a critical barrier that goes back protecting that, and then we've used a tape to tie into that. The most important thing to notice about this is we have a wood fiberboard insulation that is directly against our framing because it's all, you know, organic biogenetic material, but it needs to be protected from the elements. So we've used a Siga MyVest high performance membrane on the outside of our thermal barrier here. This is still an organic product. It's Canadian made, highly vaporable, but it also in long-term weather can delaminate and needs to be protected because it is a wood byproduct. Has a fantastic R value and resistance to heat flow. It's nice and hard to have a nice flat wall, and it's a joy to work with and cut, but you need to protect it. We still followed this up as a weather-resistant membrane and an air barrier to a high-performance sill membrane. We've added a capillary break in here just to mitigate any thermal convection or looping that could happen underneath here that could create moisture, but still allows sub-sill drainage on the outside. It's important to notice when you're using these high-performance membranes that they do have a great capability to bend and mold around corners in one piece. But if it's under stress, you should use some sort of material as a retention gusset to hold it down so it doesn't curl back over time. What we've done to enhance the thermal continuity on this build, even though it's not part of the air barrier, we've added a small layer of rock wool around the buck to encroach onto the window frame, just so you get greater levels of high performance. But we're primarily going to talk about the air barrier here.
Hey, Cody, I'm just going to jump in here, and you'll have to come back to another webinar for this. But you know, the wood fiber insulation is behind our water-resistive barrier because it's wood. But for that detail around the window, we wanted something that could be added at the end, and that could be added on top, on the outside of the water-resistive barrier. So that's why we switched from wood fiber to mineral wool. A product that is capable with dealing with more water and more moisture. We're trying to focus on air barrier, so we're not going to go into the details, but you know, little details like this can make a huge difference. Yeah,
and one difference that is probably important to note on this detail is because of our air barriers on the outside, we wanted to create a renewable detail so that if you ever had to change the window out, you don't have to affect your air barrier. So you're not handing off a future problem to your homeowner. So these are just parts of the thought process that you need to go down to ensure that you have a product and that you have a long lasting home, which is the point of a performance building. So again, we're continuing up to the top of the window. We've detailed all our corners. And in order to make this connection, we do actually have wood integrated inside, and that's just for the facade connections that are all thermally broken. Our air barrier continues around the exterior rock wool, because you can see that this insulation layer actually bridges over the window so you don't have any thermal losses. Air barrier ties around to the inside where we have a vapor retarder paint this one has a high-performance membrane on the inside. So where we didn't use poly because of the footprint of plastic, we've used a high-performance smart membrane on the inside to handle air and moisture, so vapor retarder level as well. We've managed it in the same way that Alex wanted to take note of. We've used a tape as a receiver that goes directly onto the wood. It's vapor open, highly durable and flexible, and very versatile in these sort of transitionary connections, because you're going from wood to wood through your top plate, taped to your smart barrier, with another interior smart tape. This is a definitely robust system that is actually carbon negative in its total calculation. The insulation on the interior looks a little different than the stuff that you've seen. It's a hemp bat insulation. So it's just another example of the many paths and manners that you can choose to build walls. We're moving towards a great discussion of a toolbox you can use, but pick and choose what works for you, what you like to work with, and what will work in your climate.
And again, you know, all the walls that Cody introduced in only a few minutes, as I said earlier, have two things in common. They're thicker, so they have more insulation, higher effective R values, and they have a continuous air barrier. One thing I forgot to mention is that with NRCan and RDH, we actually have been working at producing a series of videos on all the walls, and we're going to publish those videos potentially even better before the guides get published. So again, Ryan, I'll keep you posted on that, but you'll get an overview of what Cody told you and more through those videos that are going to be free for the public to just watch online. Cody, before I let you move to the phase 2 of our presentation, there's a few things that you showed that were of interest to me. So and the other thing too is Vanessa is reminding me we have to answer questions. So if you've asked questions, just be patient. Give me 2 minutes, but we will for sure do that. Can you turn, or maybe Mary walks you to the inside of that wall? Ashley said something in his presentation I thought was quite interesting. An air barrier needs to be continuous. A vapor barrier, not so much. You know, and maybe Mary, you come here for a second before we do that. In this wall, for example, we have a lot of acoustic sealant all around our poly. So the poly is the vapor barrier, very traditional build. Most people don't understand that you actually don't need the acoustic sealant from a code perspective. So if you're trying to deal with your vapor through a poly system, as long as the poly is installed on the entire surface of the wall, it actually doesn't have to be sealed on the edges from a moisture diffusion control point of view. So if you see any poly that's been sealed on the edges with acoustic sealant, in this case, if we go back to this one with tape, what it most likely mean is that the person, if the person knew what they were doing, was trying to build an air barrier. And so what I wanted to kind of point out to you guys, and maybe it's just a repetition of what Ashley said, having a double vapor barrier is a very potentially risky or very risky thing to do. Having a double air barrier is not a problem. It's just adding redundancy to your systems. And so both this wall and this wall have been built with a double air barrier. So our primary air barrier is on the outside, but we also have an inside our internal air barrier. And we did that on these two walls because both of them was using a biogenic insulation material, so cellulose and then wood fiber. And everybody was worried about the potential impact of moisture into those products that are more or maybe less resistant to moisture. And as Ashley said, there's a lot of moisture that can travel through air leakage, not through diffusion. And so a double air barrier was not necessary, but was a nice addition that made us feel a little bit better. Maybe we pause here. I'm gonna maybe leave Cody on camera, go to the questions. Oh, I see them on the screen here.
Well, Alex is going to the questions. I just wanted to finish one thought. When we're talking about exterior insulation and how it can affect air tightness, this one, because it's on the inside of our air barrier, you're not really getting a great factor of added improvement. But when you go to a single layer of insulation, whether it be vapor open or vapor closed, once you've applied this onto your exterior air barrier, you can actually improve your air tightness ratings by a compression factor. If you're doing more than one layer and you've staggered your joints, you've actually stopped any chance of air transfer getting even to your air barrier or minimized it greatly. I'll throw it over to Alex to answer some of these questions before we move on to the next part.
Okay, so it's always a bit of a challenge to monitor questions through a chat room. So I'm going to try to maybe sometime paraphrase to group questions that are similar. So the first one I think we answered was, can you have more than one air barrier? So the answer is yes. So the next question I think I have here is, how far over the top plate does the air barrier lap?
Yeah, so when we're talking about self-adhered membranes, there's still simple principles that you have to follow. So when you're using a tape or a peel and stick, 2 inches is a preferred lap. So we've used a 4-inch tape with a split backing, so you can evenly transfer the corner. If you're using a urethane sealant, it's a small bead. It doesn't really require the 2-inch minimum lap, but you want to take certain care that that bead is continuous and pressed down tightly. It's not my preferred method, but it works.
Cody, if I installed Tyvek, let's say in this case, I went for a fully interior air barrier strategy, and my Tyvek is installed only for water, water management purposes. So it's a water resistive barrier only. Mm-hmm. What do I need to know when it comes to overlap and taping? I don't think you have to tape horizontal. Let me know, what do I tape? What do I do with overlaps if it's only a water resistive barrier?
Weather resistant barrier, you want to follow all manufacturers' recommended product you're using. Most people are probably more familiar with Tyvek. So when you're doing a horizontal lap, you want to come down 6 inches, or sorry, 4 inches. When you're doing an air barrier, you would tape that. If you're not doing an air barrier, don't worry about it. When you're doing your vertical seams, you have to come over 6 inches and tape it so you don't have any capillary action with the water traveling. But since you're already there with the tape, why not just tape those horizontal seams as well and get a better air tightness rating? Oh, sorry, Mike might have been on mute. Is that better? Okay.
So I think, based on the timing of Ashley's post, I think you probably have to repeat the whole water resistive barrier.
Okay, so just when dealing with a water resistant barrier, I'll try to go over it smoothly, is when you're doing your horizontal laps, and it's just a weather resistant barrier only, 4 inches. Always follow your product's manufacturer guidelines, but 4 inches on a horizontal loose lay membrane lap is adequate. On your side laps, you want to go 6 inches and tape those joints. In my opinion, if you're there with the tape every joint to get a better air tightness rating.
And so if we go back, and maybe Mary, you can turn by 90 degrees to the mineral wool split insulation wall, the Tyvek that was above the air barrier or above the top plate, we wanted to show here you don't have to tape it. So we got that. Would you tape it anyway?
I think it's always a good idea to tape it because you're already on the wall with the tape and you're only dealing with a cheaper cost CCMA approved tape. So why not just use a little bit more and tape those laps if you're worried about air tightness migrating through the wall. But yeah, on this sort of transition where it's a horizontal lap, 4 inches is adequate for a weather resistant barrier only.
Okay, there was a question about the green product. Ashley got the answer right. So it is a MSL fiber. The hemp insulation is a nature fiber product. We built that wall mock-up trying to use mostly Canadian-made products to minimize transportation. There are a few options around the world. There's not that many options on the Canadian side. And yeah, the wood fiber is an MSL fiber. We are going to run out of time. Cody, can you maybe quickly show us the 2 tabletop? You'll have to be very brief. You have 5 minutes, really. But,
okay, no problem. This is kind of going back to a standard sort of approach of conventional building. When we're talking about air tightness with a exterior envelope first approach, we're going to walk it through without any insulation layers on the outside. So you have your subterranean protection layer, which is also weather resistant barrier and air barrier. You've got an overlap with your weather resistant barrier, water barrier, air barrier membrane that ties in as a transitional piece to your wood frame. Now you've overlapped again. This should be 4 inches. It's smaller because it's a little tabletop. We only have so much room, but make sure that all your tape connections are smooth and planned out. You don't want any wrinkles or fish mouths in it because that could result in air loss by blow-by. You come up the wall, you have your overlaps again, 4 inches. It's a water resistant barrier and air barrier, so we tape this connection. And here's where we come up to the top of wall. This is a quick little explanation of WRB only for a standard unclimatized attic. So I'm actually gonna pull this out real quick and just show the inside. Oh, if it doesn't wanna fall over on me. So if we see the top of wall connection here, we've taped the wood before the trusses have arrived to mitigate this joint. We've taped all of our joints, and you do the same at any of your interior wall plates. And what happens on the inside is all your interior walls have starters with poly. That's a pretty standard function in the course of construction and sequencing. So wherever your walls meet your interior walls, just plan them out neatly and tidily. Take a little bit of care and attention because air is an important integral part of high performance building. And then again, when you're putting acoustical seal on, if you want to do 2 air barriers, try to put your acoustical sealant bead between the 2 plates because that's where you're going to get air loss. Make sure that it's continuous, monolithic, and done tidily. Can
I ask you, Mary, to also show the ceiling air barrier from the other side if you were to either Cody rotate? There's a black line there. It's actually electrical tape. We really don't like acoustic sealant because it's messy no matter what. So we're pretending this is acoustic sealant. And I just told you earlier, if you're using your poly as a vapor barrier only, you don't need to have that sealing. So if you see it on our mock-up, it means that it has something to do with an air barrier. So Cody, maybe I'll let you finish the discussion about transferring from the outside to the inside. So again, remember this tabletop mock-up has an exterior air barrier on the walls and at the foundation, and it has an interior air barrier at the roof level, and it's happening at the ceiling level.
Yeah, so when your red pencil drawing where you're going from the outside with your air barrier transferring to inside, you have an option of transferring to poly, which, as we all know, it's not super durable, it can be hard to work with, but actually I also showed a slide of OSB plywood being taped on the inside. That can also be done as a perfect option. plant a receiver tape here. So when you put your plywood up, you're taping to the tape, you're and then any penetration through here, you can actually create with a wood box and tape those connections rather than trying to come in with the magical blue tape to stop airflow. It all depends on what level you want to go to. Some guys are achieving good air tightness with poly on the inside. It's up to you what levels that you want to go to.
And maybe that's a point I want to emphasize. You can achieve very low level of air tightness with almost anything as long as the list of anything, each items are airtight themselves, and as long as they've been connected together. We're really running out of time. Cody, I want to show the other one.
Sorry to interrupt you. You can go for a few more minutes.
Okay,
to 11:25.
Okay,
Yeah.
we're not too tight. Okay,
Excellent.
So in the lab, and again, the code or the step code is interesting because the step code is performance-based, not prescriptive. So you have freedom to choose. In the lab, we have our preferences, and one of the things that we really like is this idea of a primary air barrier that is on the outside as much as possible, because we think that it's nice to know that that air barrier will be protected for a long time, and that renovations on the inside won't puncture that air barrier. So Cody just told you, looking at the previous tabletop mock-up, if you want to have a stronger air barrier at the ceiling level because you went for an interior air barrier for the roof or the ceiling, go with an OSB or go with a plywood. So that's one way of avoiding future holes in that air barrier. The other way is to keep that air barrier outside all around the building, including the roof, and that's what Cody is going to show you now.
Yeah, so the one that I just went over is something that you can get to step 3 quite easily with products that you already have on your site, except for maybe a couple of tapes and approaches with the ceiling. This in the wall function is taking the same approaches from the bottom up with the same critical barriers overlapped and taped to create an envelope first approach for an air barrier. So we work ourselves up the wall. The primary difference here at the truss line is we did not action into the interior of the building. We're keeping the envelope first approach holistically on the outside of the building through the entire process of this build. So how we've managed to do that is by coming up to the underside of your heel sheathing, again, taped at your truss blocking line. And then if you're not a fan of using the tapes and you want to move a little quickly and you don't want to do all these transitions of doing dart corners and taping all of this, you can do a urethane sealant to mitigate all those pinholes. Now, when you get to joints of your plywood or at the edge, because this isn't necessarily part of your air tightness assembly, we want to allow the insulation on the interior part of the roof to breathe through a cavity down through a strip similar to a rain screen approach. So it's like we've taken a split insulated wall and leaned it up on the roof. But now how do we detail this transition where you're transferring through the wood to the plywood? We've got a double-sided butyl tape that's very sticky at our joints along the heel line of your truss. When you're sheeting a roof, I find, because I was a framer at one point in my life, it's very easy and efficient to plan out your roof sheathing, and you know where these marks are. So you can either mark them on the underside of your plywood, so you know that you're adding a screw fastener through there to add a compression seal, and you're adding every one of your tail heel and plywood in the you have and remember that your roofer is going to put on for you, which is also vapor air barrier. So you can also plan efficiencies through your process, getting your subtrades there that are already doing the is all together. When you go to the end of it, it's a perfect example of your vapor barrier now transferring on vapor retarder, which only needs, I believe, 80% of up joints, and you can now do away with the acoustical sealant because you're blocking that vapor zone. I love them, by the way. It can only go direction of split up with her hold, hit your vapor vapor in one direction.
Hi, I've kind of lost my audio on my end. Can anyone hear me? Me speaking? If you can, maybe type in. Oh, hello. Okay. Well, thanks, Alex, and the crew. I kind of lost the audio, so I didn't catch the last 5 minutes of that, but I hope everyone else did.
We assign all the tasks to you, Ryan, while you can hear us.
Why, thank you. Yeah. So, yeah, like once again, I just really like to thank you. You know, both Ashley and Alex and his crew for everything you've given us today. It's a lot of good information, and I hope you know, our attendees got some good takeaway from all this. So yeah, pretty much I have one other slide that I was just gonna speak to here. So all right, so I just wanted to add, you know, as a reminder, everyone can see this slide, I'm sure. That's all good. Yeah. Okay. I just wanted to add as a reminder that, you know, oops, sorry, everyone. There we go. Reminder that building energy efficient does not have to cost a fortune. In fact, with all the incentives, you can completely offset costs almost incurred for building to the higher steps. On top of the city's Penticton's mid-blower door test refund and the building permit rebate fee, you can get all these rebates from Fortis, including a rebate for using the integrated design process. Another incentive that a lot of people aren't aware of is actually through CMHC. They have the green home mortgage insurance refund of up to 25% for a building that is 20 to 40% more energy efficient than a standard BC building code building. So home buyers could definitely benefit from this. So just kind of taking into account, if you strive for step 4 and you apply for all these rebates and such, you know, potentially you could save up to $10,000 to $15,000 for that build. So that's pretty much all I have too. Is like I said, thank you once again, you know, to the speakers. I encourage any of you attendees to reach out to either Ashley or Alex if you have more questions, or you just want to learn more or get involved in the courses that they offer. And you can also visit the website address at the bottom for any upcoming webinars and education. So that's on the City of Penticton's website. So yeah, does anyone have any other last questions for anybody? Okay. Yeah, you may have missed that. So it was asked, yeah, so Penticton is currently referencing step 3 of the BC Energy Step Code for part 9 buildings, and will be referencing step 1 for part 3 buildings come the end of this year. All right. So as you log out of this webinar, there will be a poll, a little survey. So if you please fill that out, that would be good. You need to do that for getting your CPD, and that'll be mailed out to you within a week or so. So yes, thank you all for attending.
Thanks, everyone.